In this collection of videos, we are going to work some examples with a very powerful and amazing test for infinite series, which is called the ratio test. Now, we have a lot of series tests so far, and so it might be getting to the point where you're starting to say, why do we need another test? And so in introducing the ratio test, I'd like to tell you some really cool things about it. Perhaps the biggest reason that we really need the ratio test is that up until this point, we have not had a very good mechanism for dealing with factorials when they appear in our series. And truly the reason that we're studying all these different types of series tests is because we're working towards something very big. And once we get to that very big application of infinite series, the types of series that come up naturally there tend to involve a lot of factorials. So in the future, we're really going to need to have some good machinery for dealing with infinite series that have a factorial somewhere in the addend. And all of the types of tests we've studied so far are not particularly good at handling factorials. Mostly because factorials don't fall under the domain of things like geometric series or telescoping series, and it's a lot harder for us to use limit and direct comparison tests and even alternating series tests on factorials because we're not able to translate what we were doing into some sort of f of x and just think about the continuous analog of this function. Factorials are really only a thing that at this level makes sense when we're taking a whole number like 5 and looking at 5 times 4 times 3 times 2 times 1. The idea being we take the number we're at and we multiply by 1 less than that until we reach 1. If we were to try to extend the idea of a factorial to something like pi, what does it mean to compute pi factorial? We'll never reach 1 by subtracting 1 from that initial value repeatedly. So factorials don't have a good continuous analog at this level, and that makes things like direct and limit comparison tests very difficult on factorials. But this ratio test that we're about to introduce is beautiful at working with factorials. Now, that doesn't mean that you have to have a factorial as part of the addends in your infinite series in order to use the ratio test. There are plenty of other times that we can use the ratio test. As we'll see, you're free to attempt to use the ratio test on any series you would like, but in particular, the ratio test is a very good candidate for infinite series that have factorials in the addends. So let me state what the ratio test is before working out an example. Suppose that we have an infinite series with addends a sub n, and unlike some of our other tests, all we're assuming is that this is a series. I don't care if the terms are positive or negative or alternating. What I'm going to do is take a look at the limit as n is approaching infinity of the absolute value. Again, I need those absolute values because I'm making no requirements on whether or not these terms are positive or negative. So I want to throw some absolute value signs around the ratio of the next term to the current term. I want to find a formula that expresses that ratio, take its absolute value, and then look at the limit of that as n is going to infinity. Whatever value that is, we're going to call rho, which is a Greek R, but looks like a P, rho for ratio. And we're able to fall into one of 3 cases. If the ratio that we get as a result of this limit is less than 1, then this series is going to converge, and it's going to do so absolutely because we threw absolute value signs around the ratio of the terms and got this result. On the other hand, if that ratio that we obtain is a value that's larger than 1, we can conclude that this series diverges. Last but not least, a test this powerful is going to come with a catch, or else it would just be the be-all, end-all of series tests, and we would just use it every single time. So the catch that comes with the ratio test is that if we do this process of looking at the limit as n goes to infinity of the absolute value of the ratio of these subsequent terms, which is a lot of work to do, if we do all of that work and end up with a ratio of 1, then the ratio test is inconclusive. And that's the catch. We occasionally will apply the ratio test to a whole lot of work and end up with a value that is entirely meaningless. In other words, we can find examples of series and go through all of the work to find this row. The row ends up being 1, and it turns out that that series is convergent. And we can do the same thing with a divergent series. Go through all the work of applying the ratio test, get a row value of 1, and it turns out that through other mechanisms we're able to show that the series is divergent. So if you get a row value of 1, it means absolutely nothing other than that you've wasted your time and you need to go find another approach to this problem.